Hello everyone, welcome back to the channel. So in our last video, we went deep into text condition diffusion models. We ran everything manually, component by component, to really understand how they work. If you missed that, I've linked that in the description and in the I button. Today we are tackling something really exciting, which is control net. So here is the problem. Here's the problem with the regular diffusion models. You give them a text prompt, they generate an image, but you don't really have control over the structure, the composition, or even the exact pose of what gets generated. Sure, you can use Inpainting or image to image diffusion to get some control, but it's not precise. Sometimes the model just ignores your prompt entirely. The control net solves this, and we are going to see exactly how. So, what is a control net? Imagine you draw a simple sketch like this, just rough lines and shape. With control net, you can use that sketch as the structural guide, and the model will generate completely different images that all follow your sketch structure. However, they all will have different styles, different details, but the same basic composition. You can use depth map as your guidance. You can use Canny edges to follow specific line contours like this. You can use segmentation mask as well, and also human pose, where you can generate people in exact poses. One thing to note here is each control net model is trained for one specific type of control. If you are using, let's say, a Canny H based control net, it will only be able to take this Canny H as the control signal. But if you want to combine two or more signals, then you have to use two or more control nets as well. So here I have given the link to the technical paper that first proposed the control net. It came out in 2023, and since then we have seen variations of control net for different base model like Stable Diffusion 1.5, Stable Diffusion XL, Flux, SD3. So let's see the basic operation of how this works. Now let's try to understand the basic principles of the control net and how it works. The core idea is very elegant. You start with your base Stable Diffusion model, basically a unit that takes the input latent, the text embedding, the time step embedding, predicts the noise that needs to be removed from this latent vector. The control net adds some trainable copy of the unit's encoder layer, especially the down sampling block and the mid block. These copies start with the exact same weights of the unit here, but there are some zero convolution layers which are being added, and all these weights are trainable. So as the training progresses, these weights do change. So here's the most clever part. They add zero convolution layer at the beginning and at the end of these copied blocks. So why these zero convolutions? Because their weight and biases are initialized to zero. This means at the start of training, they have basically no effect. Whatever is the output you get, it will be zero. But as the training progresses, they start changing. It protects the pre-trained model from random noise gradients. As training progresses, these zero convolutions learn to scale the control net's influence appropriately. During the backpropagation or during the training, only these weights are updated and these weights remains the same. You see, which is identified using the locked signal here. One very important part is this conditioning signal. This could be your Canny edges, the pose, the depth map, whatever gets fed into the control net copy. This conditioning signal goes, so initially the conditioning signal is something like this. An image, let's say 512 cross 512, it goes through some convolution layer inside the control net and is being fed into the control net block. There is also another important thing that you can control the strength of this control net, that how much effect it will have during the generation. If this, whatever the activation you get from here, if you multiply that with 0.5, then you will get 50% of the control net's effect. If you multiply that 1, then you get 100% of the control net effect. Now let's write some code. The Diffusers library makes this incredibly easy with the Stable Diffusion control net pipeline. All the other libraries are pretty much same to what we have been using till now. Here we set the device to be CUDA. This is the model ID and this is the control net ID. This control net ID comes from this repo, and this is the one of the author of the control net paper, so you can trust this repository. First, you would like to get the control net model, so you use control net model dot from pre-trained, and you get the ID of the control net, which is this one. First, we are starting with the Canny edge, so that's why. In this repo, you will find different versions of control net, which can be pose, depth, segmentation, all of them. We'll load our pipeline. In this case, we are using Stable Diffusion Control Net pipeline and the ID of the base model, which is Stable Diffusion 1.5. Another additional part we are passing in is the control net. So this control net will be taken from this one, and that's how our control net will be loaded. The control net pipeline will be loaded. We are changing the scheduler to UniPC multi-step scheduler because this is what proposed in this repository. So now let's run this one. It's been loaded. Now let's process our input image. So I use this load image function from diffusers to get an image. I resize it to 512 cross 512, and I want this images structure to be followed during generation. So as I'm using a Canny H control net, I have to convert this image into a Canny H. This is the code I use for that. Here, these two are important. The threshold 100 and 200. Lower the first threshold to, let's say, 50, and you'll see you start getting more texture. But if you increase it to, let's say, 300, you start getting less amount of texture. So it's up to you that how much texture you want to conserve. I'll just let it be the default. All right, this much texture I want in my generation. Play around with these threshold. If you're trying to capture fine details like eyes or fingers, you'd want lower thresholds. For general composition, higher threshold works better. And now we'll start generating an image using the control net pipeline. So for that, we'll pass in our prompt, the number of inference steps we want to do, the control image, and a random generator so that we get reproducible results. Go ahead and run it. Now we get a blue bird that follows the exact structure of your Canny H. The composition matches perfectly, but the style, colors, and the details all are generated fresh. So now let's see something cooler. I can use the same control image but different prompts and see how those different prompts generate different images. So the prompts are like a blue paradise bird in the jungle, a red paradise bird, a yellow paradise bird, a black paradise bird, a white paradise bird. So let's see. Yeah. So you see, this is the blue one, this is the red one, the yellow one looks pretty realistic, the black one, and the white one. So you see, the structure is still kept intact, but however, the other styles are being changed. So here it demonstrates the power of control net. Now we'll see how to control the strength of the control net. What if you don't want the full control? Then what if you don't want the control net to have a lot of effect on your generation? You want to give your model a little freedom during generation. Then you can control that using the strength parameter, which also called the control net conditioning scale. So if I generate for 10 different conditioning scale ranging from 0.1 to 1.0, you get images something like this. The prompt is still a yellow paradise bird perched on a branch at sunset. So when the value is 1, the model strictly follows your control net image. However, when the value is very less, it mostly ignores the structure. It just follows the prompt. What I found is somewhere in between 0.5 to 0.8 is ideal because this has enough structure to guide the generation, but enough freedom to create something natural as well. Another very important application that's probably you're gonna see if you use control net often is you can combine this with the inpainting. So we have seen in detailed inpainting in our previous video. If you haven't checked that out, I'll link that in the description. We use the inpainting with Stable Diffusion. We'll import Stable Diffusion control net inpaint pipeline, and we'll do the same thing. We'll first import we'll download. So we'll import a control net and then we pass that control net to this Stable Diffusion control net inpaint pipeline. Our model ID still remains the same. Then along with the Canny H, we do another thing, which is we generate a mask. So here I want to do inpainting only in this rectangular region, and I want to keep all the other region in the black as it is. And now I'll run my control net inpaint pipeline. But here, so this is going to be my prompt, number of inference steps, the reference image, which is this one, control image, which is this one, and the mask that I just created. So we get something like this. A red paradise bird, you get only inpainted only in the region that you have specified, and rest all remains the same. But another extra parameter that you can handle here is strength. That means this strength, the strength parameter determines how much noise is added before denoising. So for example, in the default case, the strength value is 1. That means it will add all the noise it can in this region and start denoising from there. However, if you reduce the strength parameter, then it will add less amount of noise and then start denoising from there. So what it does during generation, it helps conserve the structure of the image more. If you add less noise, then it keeps the structure intact. So if you have like strength value of 0.5, then we can keep some of the original information, and with 0.1 it keeps most of the original information. And now I'll run this with different strength value. The change is only going to happen in the masked region, and you see here, as the strength increases, we start seeing more and more change. For example, here there is absolutely no change. Here you start seeing a little bit of change. Here you start seeing the green more, and finally a lot of green has happened on the basically the head of this bird. So this is how you can control the generation using the strength parameter. All right. So if you are just using ControlNet as a tool, let's say in Comfy UI or Automatic 111, then you can stop here. But if you are a machine learning engineer who wants to understand what's happening under the hood, let's dive deeper. So to understand everything, let me restart my kernel and import all the components that are being used individually. So here I'm importing the variational autoencoder, the unit, the tokenizer, text encoder, the scheduler, and the ControlNet model. I put the VA unit and text encoder into the GPU, and the ControlNet also into the GPU. All right, now comes the denoising part, that I want you to understand that what is happening when we are just calling this pipeline. It looks very simple that, okay, we call the pipeline, it does a denoising loop inside, and starts from random noise, and it keeps on getting improved. I'm not talking about the ControlNet Inpaint pipeline. I'm talking about the basic ControlNet pipeline that we saw before. Now we want to run the denoising loop manually, and what is happening inside whenever we call the pipeline. I have discussed in this denoising loop of normal text to image diffusion model in the previous video. If you have not checked that out, I highly recommend you do. Now let's see. First, we are getting the latent, then it starts with a random tensor like 1 cross 4 plus 64 cross 64, because this is the 4 channels what the unit expects. The 64 cross 64 can change. There's no problem with that. This is the prompt. First we'll tokenize the prompt. This is the tokenized prompt. Then we'll pass it into the text encoder, the clip encoder, to get the text embeddings. All right. And another important part which was missing in the last video, that in the last video, we did not need any conditioning image, but here we need a conditioning image, which can be the Canny edges for this ControlNet. Here I'm just taking a random tensor of size 1 representing the batch. 3 is the 3 channels, 512 cross 512. Then this is the denoising loop, you can say. So we pass in the latent, and the unit should give us the predicted noise. Then we'll use this predicted noise to remove from the latent. But before that, this latent goes through the ControlNet, and what it gives us the mid block residual samples and down block residual samples. So what is this? This is exactly this part. So this is the mid block activation, and this is the down block activation. Because this is a unit, all the activations from the down block directly added in the up block. During that addition, we also combine the output of the ControlNet. So what other input are there in the ControlNet? Of course, the latent vector, the latent tensor, the time step. This is a random one I took just to show that how one step happens in the ControlNet. The text embeddings, the conditioning image, the conditioning scale, that means how much strength you want to give. And this is like written dictionary. It's not very important that whether you want to give this one as a dictionary or not. Then you get the mid block and the down block residual samples. And in the unit, before we had the latent sample, the time step, the text encoding. So this 3 part. This is the text encoding, the text conditioning, and this is the time step. But now we have this 2 part, the 2 extra part, which is this down sample, residual sample, and mid block, which we got from the ControlNet. And this is how the ControlNet interacts with the unit. And finally, we get the predicted noise. Let's run this. Okay, so I have to import all the components, and now I'll run this. It ran successfully. If you see what is in there in the down block sample, so this is the size of all the activation. So you see, this is the first down block, the second one, and the third one, and this is the mid block. Now let's see the denoising loop. To get started with the denoising loop, we are also going to use the classifier free guidance. So we need a prompt and an empty prompt so that we can use this empty prompt to guide the generation. We'll tokenize it, then we'll convert it into text embedding. But now we have 2 samples, 2 text conditioning. Then now is the time to process the conditioning image. So this is the Canny edge of this image that we just obtained, and then we use this ControlNet image processor, which is nothing but just a pytorch image processor which converts the image into 0 to 1 value and pytorch tensor. And as we are using this text prompt are going into the model, then that's why we replicate the control image twice. Now let me run this. And this is our denoising loop. In the denoising loop, what happens? This is our latent tensor. This is 4 cross 64 cross 64. And in the denoising loop, we of course copy it twice because we are going to do classifier free guidance. Then we pass it into our control net and the unit. We get the predicted noise. Then we divide the predicted noise into with text and without text. Then we apply the classifier free guidance, the predicted noise we get. And using this predicted noise, we remove this predicted noise from the latent using scheduler.step. So this latent now has less noise than we started with. And this loop goes on until we go through the entire time steps. Now we got the image which is following the structure of the control net. So this is what happens inside the control net pipeline. Of course, you can go deeper by looking into what is happening in this control net, but the overall schematic remains consistent. So that was all about control net. From a high level concept to a very low level implementation, you can control structure with Canny edges, depth, pose, and more. You can combine it with Inpainting for region specific control. You can tune the strength to balance between control and creativity. In the next video, we are going to explore the open pose control net, specifically generating images with precise human pose. And we'll also look at combining multiple control nets together to get even more control over our generation. If you found this helpful, hit the like button and subscribe for more deep dives into diffusion model using diffuser. See you in the next one.